students. We have reached lesson 5-6, which is called the quadratic formula. And the quadratic formula, you may remember from Algebra 1, is a little formula that we can use to solve quadratic functions, to solve quadratic equations. And you're probably thinking, well, what do we need the quadratic formula for? We seem to have found lots of ways to solve quadratics, and why do we need another one? Well, hopefully by the end of the lesson today you'll see how this is just another important tool in our repertoire of how to solve quadratic equations. And so this table that you'll see on your first page of your lesson notes really is a way of kind of putting all the ways we know how to solve quadratics together and seeing when one way is best, which tool is best to use in each situation. So back when we first started talking about quadratics, and now it seems like a really long time ago, we used graphing as a method, and this is when we used it. Only when approximate solutions or number of solutions is needed. So unless we have integer solutions, that we could maybe use our graphing calculator and find in the table, graphing is really not a valid way to solve if you want actual solutions, because you can really just approximate the solutions, maybe by tracing on the graph, something like that. Or maybe if you just wanted to be able to look at the graph and be able to tell how many solutions does it have, or does it even have any real solutions. See, for example, let's say I wanted to just approximate solutions to something like this: 2x squared plus 5x minus 14 equals 0. And I want to know where the approximate zeros are. If I graph this and, say I use the trace feature or something like that, I would see that the two solutions to this quadratic are approximately negative 4.2 and approximately 1.7. And I can also look at the graph and see that there are actually two real solutions. So that's where we might want to use graphing, is when we just want to approximate solutions that are not exact nice values like integers or finite decimals, or we just want to know how many solutions, if any, real solutions that there are. Now, a lot of the time we've used factoring, especially earlier on in this unit. And we used factoring when the c of ax squared plus bx plus c is equal to 0. And if the c was equal to 0, if that c was 0, then we would have just a ax squared plus bx, and we might want to just factor out the greatest common factor, and then set the pieces equal to 0, or if the expression was easily factorable. So we've used factoring a lot, and it still is definitely a preferable method than anything else if it's possible to factor very easily. So we would want to use that in cases like this. Something like x squared plus 4x plus 3 equals 0 is easily factorable because I can find the two binomial factors I'm looking for, two numbers that multiply to 3 that add to 4. And so I know the two binomials both start off with x, because x times x is x squared. And 3 times 1 is multiplies to 3, and 3 plus 1 is 4. So your factors would be x plus 3 and x plus 1. And then you could set each of these pieces equal to 0, and that would get your solutions of negative 3 and negative 1. And so, that is a viable option when something is easily factorable, or if, again, you have a constant term that is 0, which would then you do greatest common factoring. Now, we've also used the method of square roots, and this is when we use square roots. When the b in ax squared plus bx plus c is equal to 0, in other words, you don't have an x term, you just have an x squared term and a constant term. That's, gives you the opportunity to isolate the variable and take the square root of both sides. Or when your equation is a perfect square trinomial. Some examples like this: 4x squared minus 16 equals 0. So you could isolate that x squared by adding 16 and dividing by 4, and then you could just take the square root of both sides. Or if you had something like x squared plus 10x plus 25 equals 50, because, then this piece right here is a perfect square trinomial, which you could then break it down into its two binomial factors, which should be identical. This left-hand side would be x plus 5 squared, and then you could go ahead and take the square root of both sides and go from there. So those are examples when you would want to use the square roots method. Now we also learned the completing the square method, and we used the completing the square method in these instances. When a was equal to 1, so in other words your leading term was 1, you just start off with an x squared, and b was an even number. Because remember, with completing the square, if you wanted to create a perfect square trinomial, you had to take half of the b and square it. So if it turned out that b wasn't an even number, it made it difficult, because then you're squaring a number that is not an integer. And here's an example of where we might have used the completing the square method. So if we had something like this, x squared plus 6x equals 10, or even if we had x squared plus 6x minus 10 equals 0, and we brought the 10 to the right-hand side, either way, this would be an okay one to do the completing the square method, because all we would need to do was take half of the middle term of that, half of that 6, which would be 3 and square, and add it to both sides. And so we would be adding 9 to both sides. Adding that 9 to both sides. We could then factor this x squared plus 6x plus 9. Because it is a perfect square trinomial, it's going to be x plus 3 quantity squared. On the right hand side, we'd have 10 plus 9, which is 19, and we would just go ahead from there and take the square root of both sides and go from there, dot, dot, dot. So we would continue on and complete and solve that in that way. Now, each one of these methods that we've discussed so far, they were all very specifically tailored to certain situations. The method we're going to learn today, or I guess review today, is the quadratic formula, using the quadratic formula. And the truth is, the quadratic formula can be used to solve any quadratic equation. It doesn't matter what the a, the b, the c is. It doesn't matter if it's got real solutions or non-real, or whether it's got integer or non-integer solutions. The quadratic formula can be used in every case. It's not always the easiest way, and so it is really important that we keep in mind all of these other methods, but the quadratic formula can be used for any situation. So we really kind of want to, since it can be used for all but not the easiest, this is when it would be easiest to use the quadratic formula. When numbers are large or complicated and the expression does not factor easily. And so we'll leave this little example column open for this, because actually the entire lesson is going to be focusing on examples of when you would use the quadratic formula. So let's move on and take a look at the quadratic formula. Okay, so in this lesson we're going to be doing two things. We're going to first classify roots using what's called the discriminant. So we'll have to introduce what the discriminant is first, and then we'll also solve quadratic equations using the quadratic formula that we just talked about. All right, so what is the quadratic formula? And I might treat you with a song when we're in class together, but I don't want to have this on audio tape or any like enduring proof that I'm singing. There is a song that you may remember to help you remember the quadratic formula. Sometimes people do it to the Michigan fight song, some to Notre Dame fight song, some, Pop Goes the Weasel. But basically, if ax squared plus bx plus c equals 0, then the solutions or roots of the quadratic function can be found by using this formula. X is equal to the opposite of b plus or minus the square root of b squared minus 4ac, all of that over 2a. So the reason why we have a song to help us remember that is that's a pretty complicated equation, but knowing it by heart really will make the process go much smoother and much quicker. Now, as I mentioned, you can use the quadratic formula to solve any quadratic equation that is written in standard form, including equations with real solutions or complex solutions, which really means that if it's got a non-real part, so non-real solutions. Okay, so we discussed this thing called the discriminant. Well, what the discriminant is, it's the b squared minus 4ac part that is under the radical. So what's up here, this piece that's under the radical, that thing's called the discriminant. And that discriminant is part of the quadratic formula that you can use to determine the number of real roots of a function. And so it will tell us, it's like a diagnostic. It sort of, if we calculate that, it'll tell us, hey, are you going to get one real solution, which we know means it's one of those parabola that sits on the x-axis? Are we going to get 2, which means it crosses the x-axis twice? Or are we going to get no real solutions? That means one of those parabolas that either opens up and is above the x-axis or opens down that's below. And so whatever you get for a value for that discriminant, that's how you can tell the type of situation you have. This table details it. So the discriminant of the quadratic function ax squared plus bx plus c equals 0 is b squared minus 4ac. And if b squared minus 4ac is greater than 0, in other words, if you get a positive number, then that means you have 2 distinct real solutions. So if you get a positive discriminant, that means that graph is going to cross the x-axis 2 times. There's going to be 2 distinct real solutions. Now, if the b squared minus 4ac is equal to 0, so if it's exactly 0, that means that there is just one distinct, so if you get 0, that means there's just one distinct solution, and that's because that parabola is sitting right there on the x-axis, so there's only one place that it crosses. Where over here, when it was positive, it means it's going to cross 2 times. It's going to have 2 real solutions. And then finally, if the b squared minus 4ac is less than 0, in other words, if we have a negative number, for our discriminant, that means there's 2 distinct non-real complex solutions. So that means there's not real solutions because this parabola never crosses the x-axis at all. And a real quick note here, make sure that the equation is always in standard form before you evaluate the discriminant, and really before you try to use the quadratic function. So you want it to be in the form of ax squared plus bx plus c. Okay, let's move on and take a look at how we can use the discriminant to tell how many solutions, if any, that our quadratic equation will have. All right, so this example says find the determinant, actually that should say find the discriminant and determine the number of real solutions. There is something called a determinant, but this is actually the discriminant. And it would make sense to call it the determinant because it does determine how many solutions you have, but it is called the discriminant. So that means we want to find the b squared minus 4ac. And then that table tells us if we've got a positive value, it means there's 2 real solutions. If the discriminant turns out to be 0, it will have exactly 1. And if it's a negative number, if it's less than 0, that means that I have no real solutions. So let's take a look at these examples. So on A, let's see, our A, this is in standard form, and our A is 1, our B is 3, and our C is negative 7. And so, negative 7. And so the discriminant, the b squared minus 4ac, would be, let's see, b, which is 3, so 3 squared, minus 4 times 1 times negative 7. And that turns out to be 9 minus negative 28, which actually is a positive 37. So I got a positive number, and so since it's positive, that means that there are 2 real solutions. Okay, so I think we're ready, because that process is pretty simple for a couple you-try questions. So what we're going to do is have you identify the a, the b, and the c, calculate b squared minus 4ac, and then based on what you get for that, tell how many solutions there are, whether there's 2 real, 1 real, or 2 non-real solutions. So go ahead and pause the video now, calculate the discriminant for B and C, and use it to tell the number of solutions that you have and what type they are. Are they real, non-real? Is there 1? Is there 2? And so on. So go ahead and pause the video now. Okay, so in B, the discriminant's value was 40. Just be real careful when you're squaring negatives, remember, because if you didn't get 40, you might have not put parentheses around your negative 16 when you squared it. But you should have gotten 40, which is a positive number, and that means there's 2 real solutions. And in C, you had to make sure that you rewrote it in standard form so that you saw that the B was actually negative 1 and the C was 8. But then I've got a discriminant equal to -95, which it's a negative number. That means there's two non-real or complex solutions. Okay, so let's go ahead and take a look at the entire quadratic formula and use it to solve some quadratic equations. So example A says find the zeros of the following using the quadratic formula. So the first step is to set f of x equal to 0. So we know that anytime we want to solve, we want to find the zeros. We're going to put in 0 for f of x, and then we have to first identify the a, the b, and the c. So let's see, our a for this is 1, because there is no number in front of the x, so it's a 1. Our b is 3, and our c is -7. And so when we use the quadratic formula, it goes like this. We'll rewrite it real quick. So it's the opposite of b plus or minus square root of b squared minus 4ac, all of this over 2a. So that's what the x values will be equal to. So x is equal to the opposite of b. Well, b is 3, so that's -3 plus or minus. What that plus or minus in the quadratic formula does is it takes into account that when we take the square root, there's always a positive and a negative version. So that's why right after that plus or minus, there's the square root of the b squared, so that's 3 squared, minus 4 times the a was 1, the c was -7, all of this over 2 times a, and the a was 1. So now let's simplify this a little bit. So I have -3 plus or minus, well, under that radical, the 3 squared minus 4 times 1 times -7, you may recognize that from the example above, but that turned out to be a positive 37 under that radical, okay? And then all over 2, because 2 times 1 is 2. Well, there's nothing I can do to simplify that square root of 37. So what that means is my two solutions are -3 plus the square root of 37 divided by 2, and -3 minus the square root of 37 divided by 2. Now those are real solutions, so those are exact values, because the square root of 37 can't be simplified and it's not a perfect square. But if I wanted to approximate these, I could use my calculator to do that. I would just have to type in -3 plus the square root of 37, see what that is, and divide it by 2, and it turns out that it's about 1.54. So that's approximately the one solution. Now the other one, -3 minus the square root of 37 divided by 2, would be approximately -4.54. Now that's why we couldn't have used factoring to do this. These are not integer values. They actually are irrational numbers, and so we at some point have to round them. So leaving those exact really is probably the best way to go. But knowing what they are approximately equal to, that gives us a better sense of where this parabola is actually really crossing the x-axis. So there's value in knowing that. All right, let's take a look at another one. So this time my function is 2x squared minus 16x plus 27. And I'm going to go ahead and identify the a, the b, and the c. And I'm going to also put in 0 for, this is sort of a formality. We're just sort of going to replace f of x with 0. So my a is 2, b is -16, my c is 27. So if I use the quadratic formula, it's going to look like this. The opposite of -16, so it's the opposite of b, so b is -16, the opposite of that is +16, plus or minus the square root of, let's see, my b squared, so that's going to be -16 squared minus 4 times 2 times times 27, and that's all over 2 times 2. So let's clean that up a little bit. We'll find out what's under the radical. So that's 16 plus or minus. Under the square root, that turns out to be 40. And again, you may recognize that that's from the prior example where we found the discriminant. And then divided by 4. Okay, well, let's see what we can do to clean this up. Well, first of all, I know that we could simplify the square root of 40. It's got a perfect square factor of 4, so I could rewrite this as the square root of 4 times the square root of 10, which I know if I take the square root of 4 that is plus or minus 2, but I don't need the plus or minus, it's already got it in the quadratic formula. So that's 2 square root of 10. So this is really 16 plus or minus 2 square root of 10 divided by 4, which actually means I can simplify this a little bit because that 4 that's on the denominator is really the denominator of both pieces. That means it's the denominator of the 16, so this really means 16 over 4 plus or minus 2 square root of 10 over 4, which now I can reduce this. I can reduce the 16 over 4 to 4, and then plus or minus, and then I can cancel out this 2 with the 4, and makes my denominator 2, so then that's the square root of 10 over 2. So that really means my two solutions are 4 plus the square root of 10 divided by 2, and 4 minus the square root of 10 divided by 2, which the approximates to those they are approximately equal to about 5.58, that's the one that's the 4 plus the square root of 10 divided by 2, and the other one is approximately 2.42. So here are my two solutions. They are approximately 5.58 and 2.42, but the best answer to give is the exact solution, which is 4 plus or minus the square root of 10 over 2. Now, if you recognize C was the same as C above when we found the discriminant, this one turns out to have two non-real solutions. The discriminant turned out to be negative 95. And so we're going to go ahead and do this one together rather than leaving for you as you try. So again, we want to always identify the A, the B, and the C. The A is 3. The B was a negative 1. Because this just is not set up in standard form. And the C is 8. So let's do the quadratic formula, the opposite of B. So it's opposite of negative 1, which is 1, plus or minus B squared minus 4AC. Well, of course, we did that already. So I'm just going to draw your attention to that part that we did right up here. And we got negative 95 all over 2 times A. Well, A is 3, so 2 times 3 is 6. So I end up with 1 plus or minus the square root of negative 95 over 6. Now there's not much I can do to really simplify this except for to take out that, we have that negative. We could really write this as 1 plus or minus. We can break up that square root of negative 1 times the square root of 95. 95 doesn't have any perfect square factors over 6, which then the square root of negative 1 is I. So I could write this as 1 plus or minus I square root of 95 and the whole thing over 6. And there's really nothing more I can do to simplify that, because I can't really reduce anything. I can't take anything out of the 95, and that really is my solution. And I guess you can probably see why we call these complex solutions now, because they look pretty complicated. But that really does it for today's lesson. So, if there's anything you're struggling with or just have any questions, be sure to make a note and bring those up when I see you in class. So, by the way, one last thing. We included in the guided notes a sort of like a proof of the quadratic formula. And basically, it just shows you the progression of how to get the quadratic formula from standard form of an equation by completing the square. So I think it's interesting to include. It's pretty complicated looking, but I mean, if you take a few moments and read through it, I think it'll make sense where all the parts of the quadratic formula come from. And I think it's pretty interesting to note that as you're kind of working through it, you come to points like, for instance, here at this step, second to the last step, where you have this opposite of B over 2A, which you may remember is the x-coordinate of the vertex. So that's kind of interesting to see how that's built into the quadratic formula. And if you remember, we talked about that when you have a quadratic function and it's graphed, and you think about the solutions, if there are two real solutions, they are evenly spaced on either side of the vertex. So if we had to, like a parabola that looks like this, and we had the vertex that was right here, we know that the axis of symmetry runs through it. And you can see that those two solutions, here and here, are spaced the exact same amount. So this space that's going either direction from the axis of symmetry is equal. And so basically what this shows you is that if you're at minus b over 2a, which is the x coordinate or the vertex or the axis of symmetry, then you could add the square root of this piece right here, this square root of b squared minus 4ac over 2a to get one solution. That would be the one going to the right. Or you could subtract the square root of b squared minus 4ac all over 2a. That's the solution that's going to the left of the axis of symmetry. And so I just think that this is really interesting to note. Although we won't ask you to do any of this deriving, I think it really does help you understand better on a deeper level where the quadratic formula comes from, number one, and really the relationship between the solutions of a quadratic and their proximity, an equal proximity from the axis of symmetry. So now that does it for today's lesson, and I will see you in class.